Okay, so you sent us a fascinating collection of these visual proofs
Yeah.
from the book Proofs Without Words, Exercises in Visual Thinking.
Yeah.
And we're going to dive into those today. I
Yeah?
love it.
It's really cool stuff.
Yeah, and it looks like you're interested in exploring how these images can kind of unlock mathematical secrets, right?
Yeah,
Without having to rely on all these dense formulas and all that stuff.
intriguing, isn't it? The idea that you can capture the essence of like
Yeah,
a really complex mathematical argument, sometimes in a single image.
totally.
It really speaks to the power of visual thinking, I think.
And it seems like you're really keen to understand how these visual proofs can kind of make these mathematical concepts clearer, more memorable.
Precisely.
Yeah.
But before we get lost in all the amazing images,
Right.
I think maybe we should take a step back
Yeah.
and just define what we're talking about here.
Okay.
What exactly are proofs without words?
Right.
You know?
Well, the book's introduction kind of says that they're visual representations that almost let you see the logic of a mathematical argument, you know?
Yeah.
So it's almost like a proof by picture,
Yeah.
you know, where the picture itself is guiding you to the conclusion.
Yeah, and what's fascinating
Wow.
is this isn't some
Yeah.
brand new concept either.
Oh, really?
No, the book actually mentions visual proofs going back centuries, you know,
Wow.
from ancient China,
Wow.
classical Greece, India.
Interesting.
But they really gained a lot of traction around 1975.
Okay.
Thanks in part to Martin Gardner, you know.
Oh, right.
Remember him from the Mathematical Games column?
Right, yeah.
Yeah, he was really enthusiastic about these and kind of popularized them a bit.
That's interesting. Well, and this is where it gets kind of interesting. Are these diagrams really proofs, like in the rigorous mathematical sense, you
right.
know?
Yeah.
Because there seems to be some debate on that.
Oh, for sure, for sure.
Yeah.
You've hit on a key point there. Some mathematicians are adamant that you need that formal
Right.
logical argument, clearly defined steps.
Right.
Whereas others,
Yeah.
you know, are a little bit more open-minded
Yeah.
and see these visual representations as
Mhm.
really valuable tools for understanding, even if they don't tick every box
Right.
of a formal proof, you know?
Yeah. Well, the book even quotes Paul Hamos,
Oh, yeah.
who says, "To be a scholar of mathematics, you must be born with the ability to visualize." And that most mathematicians try to develop this ability in their students.
Absolutely.
So there's obviously something to it.
There is.
Yeah.
And I think even if a diagram,
Yeah.
you know,
Yeah.
doesn't explicitly lay out every single step
Mm-hmm.
of a formal proof,
Right.
it can still provide really powerful insights.
Totally.
You know, they can help us see connections that we might not have seen before.
Yeah.
They can develop our intuition,
Right.
help us remember things more
I
easily.
was going to say, I bet they stick
Yeah.
in your brain more than just some formula.
Yeah. There's a quote in the book from George Polya
Okay.
who said, draw a figure. It's classic pedagogical advice.
So true.
Yeah.
So true.
It's a classic for a reason.
Well, and this book is just,
That-
you know, like you said, it's a feast for the eyes. It's
Yeah.
got all these examples. It
Yes.
covers all these different mathematical topics.
Yeah.
And why don't we walk through
Just do it.
some of the standout ones that you shared, starting with
Right.
geometry and algebra?
Sounds good.
Okay.
Yeah, and what better place to start than with a true classic,
Yeah.
the Pythagorean theorem.
Yeah.
You know,
Of course.
you sent over a collection of visual proofs for this.
I did.
Fundamental concept, IBI. Some are just incredibly clever.
I was really struck by the one
Yeah.
that was adapted from the ancient Chinese text Chopei Suan Qing,
Oh, yeah.
dating back to around 200 BC.
That's amazing.
It's incredible just to see
Yeah, this.
how they used this arrangement of squares and triangles
Yeah.
to just demonstrate that relationship. A plus B exists to same 4.
Yeah, it really is a testament to the fact that visual thinking in mathematics has been around for a very long time.
Oh, wow.
And speaking of historical figures,
Yes.
you also sent over The Proof by James A. Garfield.
Right?
Yes, that James A. Garfield, the 20th U.S. president.
That's incredible.
It's amazing, right?
I know. It's crazy to think that
Yeah.
a president was doing that.
It's just amazing to see such diverse minds
Mm-hmm.
across time and disciplines
Mm-hmm.
engaging with this fundamental concept
Right.
through visual means.
Well, and it really shows how intuitive this concept is.
It does.
When you see it visually.
It is for sure.
It's like you don't even need the equations.
You don't.
It just jumps out at you.
It does.
What other
geometric gems?
Yeah, geometric gems caught your eye?
Well, the rolling circle squares itself is just beautifully elegant. It visually demonstrates how the circumference of a circle is directly related to the area of a square.
Right.
With sides equal to that circumference.
Right.
It's just a beautiful proof.
Yeah. And I love the one, the trisection of a line segment where they use the intersecting circles.
Intersecting circles.
To get a perfect third, you know?
Yeah.
It's like, how did they come up with that?
It is amazing, like, how they figured these things out.
Yeah.
But they did.
It's pretty cool.
It's pretty amazing.
And then the vertex angles of a star sum to 180 degrees.
Oh, yes.
It's just so clear.
That one's great.
When you see the diagram.
It's immediately clear.
Yeah, you're like, oh, okay.
Yeah.
Even though you might not have thought about that before.
It's not necessarily intuitive until you see it.
Right, yeah.
Yeah.
So we've seen how they can be used in geometry, but can they be used for more complex things like trigonometry, calculus, that kind of thing?
Absolutely.
Really?
Yeah, the book showcases visual proofs for trigonometric identities, like the sine of the sum and difference formulas.
Wow.
Even the law of cosines.
Oh, wow.
For example, the visual proof for the sine of the sum formula uses these triangles within a unit circle very cleverly.
Okay.
What stands out to you in that diagram?
Well, I like how it uses like the areas and the side lengths within the circle to directly represent the trigonometric relationships in the sine of the sum formula.
Yeah.
It's like the formula is embedded in the geometry.
It is. It is. And you see that idea of embedding mathematical relationships within the visual framework.
Yeah.
In the calculus proofs as well.
Okay.
The proof for integration by parts uses areas under a curve to represent the terms in the formula.
Got it.
You know, it's taking something abstract and making it something you can almost, you know, feel and touch.
Tangible, yeah.
Yeah.
That's cool.
Yeah.
And I love the midpoint rule is better than the trapezoidal rule for concave functions. Where you can just immediately see.
It's just so obvious.
Yeah.
Why the midpoint rule
why it works.
Gives you a better approximation.
Yeah.
It's a great example of how a visual proof provides this real intuitive understanding.
It really does.
It's almost like you bypass the need for an explanation.
You do.
Your brain just gets it by looking at the picture.
Yeah, like a shortcut to understanding.
It is.
Yeah.
It is.
You also sent me some for inequalities, which I thought was really interesting.
Yeah.
What are some key takeaways there?
Well, there's a few really compelling visual proofs for the arithmetic mean geometric mean inequality, or AMGM for short.
Okay.
Let's focus on the one that they call the arithmetic mean geometric mean inequality.
Okay.
It uses a simple diagram, a semicircle with a diameter divided into two segments, labeled A and B. They draw a perpendicular line from where those segments meet up to the arc of the semicircle.
Okay.
Now that creates a right triangle, and the length of that perpendicular line represents the geometric mean, which is the square root of A times B.
Okay.
Now, how do you think this proves the inequality?
Well, the diameter of the semicircle
Yeah.
represents the arithmetic mean,
Uh-huh.
which is A plus B2.
Right.
And because it's a semicircle,
Yeah.
the diameter is always the longest line.
Yes.
Right. From one point on the circumference to another.
Yeah.
So we see that the arithmetic mean, which is the diameter, is always greater than or equal to the geometric mean,
Yes.
which is that perpendicular line within the semicircle.
Beautifully put.
It's just so simple.
It is.
And intuitive.
It is.
Yeah.
The visual representation makes it immediately obvious
It does.
without any algebraic manipulation.
Yeah, it's like the image itself is the argument.
Exactly.
Exactly.
And you also pointed out the median property.
Which, that's another great example of how visual proofs can reveal these hidden connections between different mathematical ideas.
Right.
You know?
Yeah.
In this case, connecting the concept of the median to the slopes of lines in a triangle.
Exactly.
Yeah, and the sum of a positive number and its reciprocal is at least 2.
Oh, yeah.
It's fascinating because it has 4 different visual approaches.
Wow.
All leading to the same conclusion.
It's like each one's giving you a different lens
It is.
To view the concept.
Exactly.
So what does this all mean?
Yeah, that's the key question.
Yeah, like what's the so what?
The so what factor.
How can understanding these be beneficial to us?
Yeah.
Besides just thinking they're neat, you know?
Yeah.
Well, they can be a powerful tool for learning and remembering
Absolutely.
mathematical concepts, right?
I completely agree.
When you see it, it's going to stick in your brain more.
Absolutely. When you see the relationship.
It's much stickier than when you just read it in a textbook.
Absolutely.
And I think they can also help with problem solving.
Okay.
Because when you can visualize a problem, you can often see the solution more easily.
Okay.
And I think, they can also be great for explaining these ideas to people who may not have a strong mathematical background.
Okay.
It's like finding a common language that transcends all the formulas and the equations.
And especially if they're more visually oriented.
Yes.
Yeah.
Especially,
Yeah.
Instead of relying on symbols, you could just point to shapes and relationships.
Right.
It's much more intuitive for a lot of people.
Do you think exploring these visual proofs changes how you understand these mathematical concepts?
Definitely.
Yeah.
Yeah, it reinforces this idea that there are often multiple paths to the same truth.
Right.
Sometimes those paths are visual.
Right.
And they can be just as rigorous and insightful as their symbolic counterparts.
It's like unlocking a new way of thinking about math.
Yeah.
More intuitive, more creative, maybe more engaging.
Precisely.
Yeah.
And I think that's why this book, Proofs Without Words, is so valuable.
Yeah.
Because it encourages us to look at mathematics in a new light.
Right.
See the beauty and elegance that are often hidden beneath all the equations and the symbols.
It makes you wonder what other complex ideas could be made accessible and engaging through these images,
Totally.
It's fascinating.
It really is. Yeah, it really is fascinating to think about how we could use visual thinking, to revolutionize how we learn and understand things.
Yeah.
Even beyond mathematics.
Totally.
Imagine explaining a complex scientific breakthrough or an economic principle.
Right.
With a visual that just makes it immediately clear to a much wider audience.
Yeah.
That's the potential here.
I know. That's really cool.
And the book gives us a taste of that. It has some visual proofs that go beyond basic geometry and algebra.
Okay. Okay.
For example, you shared some fascinating ones.
Yeah.
For concepts in calculus.
Yeah.
Like the one that demonstrates that the midpoint rule is better than the trapezoidal rule.
Right.
For approximating the area under a concave function.
Yes, and that one's so cool because you can just see it.
You can just see it.
Like, you don't even need the explanation, really.
You don't.
Yeah.
It's so clear.
Yeah, it's just right there.
Right there.
Were there any other calculus ones that you liked?
The proof for integration by parts is really clever.
Okay.
By representing the terms of the formula as areas under a curve.
Right.
It makes this concept that can be a little bit abstract in calculus, much more tangible and easy to grasp.
It's like you're using a different part of your brain almost.
Yeah, you are.
To understand it.
Absolutely.
Yeah.
And there are also some great visual proofs for sequences and series, providing insights into things like geometric series.
Okay.
Even the alternating harmonic series, which is fascinating.
Oh, yeah, I remember that one.
Yeah.
That one was wild.
Yeah, it's incredible how they represent that visually.
Yeah, they used like rectangles under a curve.
Yeah, rectangles under the curve of y1x.
Right.
To show how the series converges to the natural log of 2.
It's just amazing to me that you can even represent that.
It speaks to the versatility of visual thinking in mathematics.
For sure.
And, there are even visual proofs for number theory concepts.
Oh, really?
Things like the sums of squares and sums of cubes.
Oh, wow.
Those really impress me.
Yeah, those were cool.
The sum of squares formula proof uses a 3-dimensional stacking of blocks.
Right.
To represent the squares.
And the cubes were in a grid, right?
Yeah, 2-dimensional grid for the sum of cubes.
That's so cool.
Both very elegant and insightful.
Yeah.
I think it highlights something really fundamental about how our brains work. We process visual information so efficiently.
Right.
When we can tap into that power, we can reach a much deeper level of understanding.
Yeah.
It's like we're bypassing the language centers of our brains.
Okay.
And connecting directly with the intuitive core.
Wow.
Of the concept.
That's a cool way to put it.
Yeah.
But I mean, can all math concepts be represented visually?
That's a great question.
Are there limitations to this?
Yeah. That's a very thoughtful question.
Yeah.
And to be honest, yes, there are certain concepts that might be difficult, if not impossible, to really convey visually. For example, very abstract algebraic structures or concepts that involve infinite dimensions might be too complex to fully capture.
That makes sense. It's like trying to paint a picture of infinity.
Exactly.
Yeah.
It's just not going to be possible to really get the full essence.
You can't really capture it.
You can't. And even in some cases, even when a visual representation is possible, it might be so intricate and so complex that it loses the clarity and the elegance that make visual proofs so appealing in the first place.
Yeah. They have to be simple.
There's a balance to strike between visual appeal and mathematical rigor.
So it's not a universal solution, but it's definitely a good tool.
Yeah, it's a great tool.
In the toolbox.
Absolutely. Especially for building intuition and understanding.
Yeah.
I completely agree.
Yeah.
And, even if a visual proof can't fully capture the formal rigor of a concept, it can still be a starting point. It can spark curiosity.
Totally.
It can inspire a deeper exploration.
I like that.
Remember the proof for the existence of infinitely many primitive Pythagorean triples.
Oh, yeah.
That combines geometry and trigonometry so beautifully.
It did.
To show how you can generate an infinite set of Pythagorean triples.
And I just love how it was like blending those two different areas of math.
It does.
Yeah, it was really cool.
Yeah, that's a perfect example of how visual thinking can illuminate these connections.
Totally.
And open up new avenues of exploration.
Right. It makes you wonder how many other secrets are hidden there.
It really does.
Just waiting for us to figure them out visually.
Absolutely.
And one of the cool things I think about these visual proofs is that they kind of transcend formal mathematics,
They do.
And they can connect with a wider audience.
Yeah.
Remember the problem of the calisons?
Oh, yeah. That one was so much fun.
Yeah.
That was delightful.
That was a great one.
It was.
And it was so easy to understand the visual proof of it.
Using a puzzle to demonstrate a mathematical theorem.
Yeah, it was just like diamond-shaped French sweets.
French sweets.
It was so clear that each orientation occupied a third of the space.
Exactly.
It's a perfect example of how a visual proof can just make something obvious.
It can.
Without any calculations or formulas.
And who doesn't love thinking about delicious French sweets?
Right.
Yeah.
That was a good word.
It's a win-win. So we've seen how visual proofs can illuminate all these different mathematical ideas.
Yeah.
But I think there's a deeper level to this.
Okay.
There's something more philosophical that we haven't quite touched on yet.
Yeah, what does it even mean to know something?
That's it. That's the question.
Yeah. Yeah.
How can visual thinking help us bridge that gap between knowing something and just memorizing it?
Yeah, it really seems like they point to a deeper kind of knowing.
Yeah.
One that goes beyond just memorizing.
It does.
Formulas and equations.
I think that's what's so captivating about them.
Right.
Yeah. In a world where we're just bombarded with information all the time.
Right.
It's easy to fall into this trap of just rote learning, just learning the how.
Right.
Without ever really understanding the why.
Yeah.
And I think visual proofs offer a way to break out of that.
Okay.
They let us connect with the essence of the concept.
Right.
See the underlying patterns, the relationships that give it meaning.
It's almost like the difference between reading a recipe and actually tasting the dish.
Exactly.
You can follow the steps and get the result, but you don't really get it.
You don't appreciate it.
Until you experience it.
Yeah. And visual proofs offer that direct experience with mathematical concepts.
Yeah.
Think back to those proofs for the Pythagorean theorem.
Yeah.
They didn't just show you a formula.
Right.
They let you see the relationship between the squares and the hypotenuse.
Right.
And it made it clear why the theorem had to be true.
Yeah. And it makes you wonder, are there other mathematical concepts that we've been learning in this abstract way that we could bring to life?
Through this.
Yeah.
I think the potential is huge.
Yeah.
Imagine students learning calculus by actually seeing areas under curves change dynamically.
Right.
Or exploring the beauty of fractals by watching them unfold on a screen.
Yeah.
I mean, it could revolutionize how we teach and learn math.
Totally.
Make it more accessible, more engaging, more inspiring.
It's like we're opening up a whole new dimension of mathematical thinking.
I think we are.
Yeah, one that speaks to our visual intuition.
Absolutely. And this idea of visual thinking goes way beyond mathematics.
Oh, totally. Yeah.
Absolutely. Whether we're trying to understand a complex scientific process.
Right.
analyze economic trends, or even design a new product.
Right.
The ability to visualize the problem can be so powerful.
Totally.
It can unlock insights, lead to creative solutions.
Yeah, imagine explaining climate change, with a series of images that show the impact,
Absolutely.
or presenting a business plan with a dynamic visualization
Totally.
that highlights, growth areas or something.
It's like we're finding new ways to communicate these complex ideas,
Right.
bridge that gap
Yeah.
between expert knowledge and public understanding.
That's a really good point.
Yeah. And in a world that's facing increasingly complex challenges,
Yeah.
this kind of clear, intuitive communication
Right.
is more important than ever.
Well, this has been really interesting.
It has.
This whole dive into visual proofs.
It's been a pleasure.
Yeah. It's really made me think differently about things.
Given us a lot to think about.
It has.
Yeah, we've seen how powerful visual thinking can be in mathematics.
Yeah.
It can illuminate concepts, spark understanding, and even change how we think about learning.
It really can. It makes you wonder,
It does.
what other hidden patterns and relationships are out there,
Yeah,
just waiting for us to find them.
absolutely. Not just in math, but in every area of knowledge.
Yeah, maybe this inspires you to look for those patterns yourself.
I hope so.
The visual essence, the simple elegance underneath the complexity, and maybe even pick up a pen and paper and start sketching out ideas.
I love that.
In a new way.
It's been a pleasure exploring these ideas with you.
It has been. Thank you.
Thanks for joining us on this deep dive into the world of visual proofs.
Yeah.
Until next time, keep exploring, keep questioning, and keep looking for those aha moments
Right.
that make learning so rewarding.